Mr. T.
Dr. Quantum Double Slit.
Quantum weirdness. The infamous double slit experiment. Understand this experiment. We first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens.
I'm so excited about
If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall.
And so that's what I showed you guys on the wall.
Are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
Ian, please don't go quantum.
An electron
It's gonna be
is
my
a
nature.
tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
All-seeing eye.
It was here that physicists stepped forever into the strange, never world of quantum physics. What is matter? Or waves?
Pragmatic that deserves.
What does an observer have to do?
I don't get it.
I don't like it.
It's marble, but moves in waves.
Collapsed the wavefront
Watch your jaw the way.
by observing.
Oh yes, of course you're agreeing with yourself.
Yeah, Mrs. Fisher turns into some weird cult.
But my new favorite phrase is what? An interference pattern.
That kind of gives you a visual on that single slit, double slit experiment.
They freeze up.
I do hope that I don't look horribly animated in 50 years.
No, you will.
You will, yeah. As well
Everything's
as,
gonna be
like,
CG.
weirdly bald in certain spots. While also
In 50
having
years,
a
we'll
lot of-
transfer
But you
all
can
of
kind of
reality
see
to
how,
vision.
Yeah,
you know,
I mean,
all
that's
be poorly
basically my
animated.
major in
Yeah.
a nutshell is that.
Quantum.
In 50 years, we'll all be transferred to the internet, and we'll all be poorly animated.
Very crappily animated.
Okay.
Only the rich people will be animated well.
What?
Only the rich people will be animated
Wait, I know Dr.
Everyone else gets
And the-
software.
Okay.
And then the poor people.
Everyone else
So, don't worry about drawing this, okay? I'm just gonna kind of show you where these equations come from. So when you have a double slit experiment, and you could have this on a small scale like I just did with a piece of aluminum foil, and you have a wave of light coming through, and then what's gonna happen, and I just picked one, I mean, you have all multiples of these. You're gonna have your brightest one right here. Your book uses a value of Y, the AP uses X, okay, they can't agree on what, it doesn't make any difference. But what the zero, whether it's 1, 2, 3, or 4, what these integers represent, and this is this M, is like if you're at the middle, M's gonna equal 0. If you're the first one out, M's gonna equal 1, M's gonna equal 2, M's gonna equal 3. So, unless you're specifically told differently, you just let M equal 1. So unless they tell you, oh, go to the second bright line or the third bright line, don't even worry about the M, just assume that it's 1 unless you're told explicitly differently. So basically what happens is this. When you're going to get a bright line, these R's are representing like so here's this barrier. This wave of energy is coming in. So what this is representing, and I drew this as a ray, this is where it's handy to treat it as a ray, and in fact, it's actually a wave, because that's what allows it to interfere, but we're going to treat it as a ray, because it's going to make the math easier. So basically, this distance from here to here is going to be R2. This distance from here to here is going to be R1. So if they're going to reinforce each other, it has to be a multiple of these wavelengths, okay? Because you can't, if you're off by like a half of a wavelength, then, or a third of a wavelength or something like that, you can't reinforce each other. So the distances that these travel is going to be a multiple of the wavelength. So if you look at a little bit of trig inside of here, and again, I'm never going to expect you to derive this equation, I'm just showing you where it comes from, okay? So imagine that you have this angle right here, okay? So the hypotenuse is going to be the distance. So what you're trying to find is this distance, is this value between R2 and R1. So if you imagine this being the hypotenuse, you're trying to find the side opposite of this, and this is representing the hypotenuse because this is, I should have drawn that, okay, that's a right angle. So this equation, that delta R equals d sine theta, comes from this little triangle inside of here. So the difference to get a relative maximum over here, where you get a bright line fringe, is based upon the fact that the differences between the lengths that those travel has to be a multiple of this wavelength, which is this m lambda. So all I'm showing you is where it comes from. Okay, that's all you've got. Now, and that's what's on your equation sheet on the actual exam. Now, your book actually has kind of another one. And it's got, they use y again equals m lambda L over d. Sometimes you see it as xn. Oh, I screwed that up. So depending on which book that you look in, it's the exact same thing. One calls it X, one calls it Y. So what this is giving you is basically the difference is how far apart these relative maximums are on a bright line, or excuse me, on a double slit experiment with where you have like a bright line spectrum. So the simplest one again is, unless they tell you something different, this is going to equal 1. Okay, so you're just going to find, like let's say you want to find the distance of the first bright line spectrum. Okay, you have the middle one. So this is going to be the distance from, this is this light coming in, here's this wall, just like they did with the screen, and you're going to try and find out how far apart these bright lines are. So this D is going to be the distance in between the two slits. Okay, that's a fixed value. You cannot change that. The L value is a fixed value because that's going to be the distance from the screen or from where the light emanates out to here. So the only thing that you can really do and manipulate is the wavelength. So this is how you can actually measure the wavelength of light. Okay, because it isn't like, hey, I can turn on a laser and then sit here and go, oh, here's this light, and I'll measure the wavelength like I can on a slinky. Okay, I can't do that. But what I can easily measure is that I can measure how far apart these slits are. Oh, okay, I can measure that. Oh, look, here. Okay, I took the razor blade, I made 2 little slits in the aluminum foil. This M is going to be, well, which bright line am I looking at? Is it the first one? Is it the second one? Is it the third one? Oh, okay, I can count that. I can get to M. I can easily measure L because that's the distance from the screen from the light source to the screen. Okay, I can measure that. So these values here, I can pretty easily measure. So if I can measure those, then solving for the wavelength, that's something that I can physically do in terms of solving for that wavelength. Because everything else is kind of like a large value that you can measure. This is what's going to get a little bit weird. So now, if you look at what happens with the units, so I've got this in meters, I got this in meters, and I got this in meters. So basically I have meters squared divided by meters, I end up with
Meters.
meters. Okay, because that has to work out as well. So it's the exact same equation. Sometimes you'll see it written as y, sometimes you'll see it written as x. It's the exact same equation. Okay?
So y and x are the distance between like the M1 and M2?
Yeah, so like you would have like a bright, here let me draw that. So you would have, if you looked at the screen, like kind of what I did back there. So you'd have, this is going to be a little bit tough to draw. So this would be like that central maximum right in the middle. And so then you'd have like other ones out like this. So if this is the central maximum right here, then the distance, the next one is going to be 1.
Okay.
And then you'd have 2, and then you'd have 3, and then you'd have 4.
So x is the distance between 1 and 0?
Yes,
Okay.
that's what you're finding. Now, if you think about it, it kind of makes sense. Because as the wavelength gets bigger, okay, what happens to the distance between your relative maximum areas of light?
Also gets bigger.
It's also going to get bigger because it has to be a multiple of that wavelength. So as this thing is traveling, okay, as your wavelength gets bigger, then the next position where they can reinforce each other would also get bigger, okay? Now, what you'll see is that this doesn't have to be a light source, okay? What we'll get into tomorrow is that you can actually, this is how they used to use navigation beacons. What you would do, somebody's light going off on the other phone. That's annoying.
Do phones do that when they're receiving?
The FBI is watching us.
You can change it.
What's up? Is it a Morse code signal? Is it that?
Someone's calling for help.
Someone's calling.
Oh,
I don't,
What did you do with the real bag?
someone's calling from California, I have no idea.
You should have answered.
But we all know Ben's from California.
It's my California connection. Okay. I don't know who it is, it's someone from California. So, now look at what happens if you shrink the value of distance. If you make those close, if you shrink the distance between the gap. Okay, let me go back to the navigation. I got confused with the navigation, with the flashing lights, like, oh my God, look, a squirrel. So, what they would do, before this was in the days before GPS, is that you would have like two navigation beacons that were emitting radio waves. Now, what's this? Do radio waves travel at the speed of sound or at the speed of light?
Speed of light.
Speed of light. Keep that in mind when you take the test. I'm just telling you.
Speed of
Someone's gonna
radio.
mess it up.
I know. So, what they would do is they would have two navigation beacons. And what they would do is they would keep track, so you would have a receiver out here on the boat. And so if you knew your boat was traveling parallel with the coast, what you would do is you would hit a point of relative maximum. So you would hear the intensity of that radio signal get louder. So basically you would just use that equation down here and you would say, oh, okay, all right. So you would know how far apart your relative maximums were, because you're traveling at a constant speed. So you could figure out this. You would know the wavelength that it's being broadcast at. You would know how far apart the radio antennas are, and they're basically acting as a light source. So then you would solve for L, and that would tell you how far off the coast you were. But you'd have to know how far apart you were in getting that relative maximum. So if you knew all that, it wasn't a precise science, but at least you could get some idea of how far your boat was off the coast. That used to be how they did radio signals. So let me see. That's it. Okay. Got through all of that. Got through all of that.
Then you gave us no homework.
It's pretty short.
How much is it?
He always says that. And then again, when it's like question.
No, he doesn't. You just haven't experienced when he hasn't said it.
But this time we have to set.
So this is an odd test because we're actually going to have material out of chapters 15, 16, and 17. So there wasn't like enough to have the test over all of one unit, so I just kind of combined them all into one big test over these 3 units.
Wow. Oh, it's all waves, so. Whatever. 1, 4, 6, 7.
I'm proud of
I'm very proud. Okay, that says 1 through 4, no.
Yeah, 1 through 4.
Okay, I will make sure.
1 and 4.
Not question
6 and 7,
It's
and then when
question
you
one
get to
dash
7,
four.
only do A through C.
Yeah, we don't want to get in the like D.
You get a D.
Probably. Probably problem. These problems are problematic.
Why is there no grade like that? Whose idea was
I know.
this?
Who did this? I think it's just
A,
that.
B, C, D, and then fail.
Yeah, because you're failure. You get an F, you're failure.
No, you
It's
really
not,
do.
they didn't choose
Only
F
in
just because it was
say
like
it
What do you mean only in degrees?
after.
It asks for radians and degrees.
Why
We don't need radius or empty useless variables.
Imagine using radio.
No, that's what we don't. Trig game.
Well, they are stupid.
Okay. So when you get to number 7, I think it asks to give you that in like degrees and radians, just give it in degrees. And then Eliza, it's 1, 3, 4, 7, 10, 12, not 1 through 12.
Thanks.
Okay,
No.
just pointed that out.
No, this one, just do the entire chapter.
So we'll review tomorrow, and then
Become the Nanolord.
test will be on Friday.
Praise be to the Nanolord.
No,
This test, it feels like it's gonna be a shorter test.